Check, check, check. Hey, Aaron. All right, guys. Just opening up office hours here. Just want to touch base if you have questions, if you've been working on the assignments, um, and if you have questions, please ask them now. Um, AP chemistry, I just sent out some more review materials for you. You might want to take a look at those, and that might help your review. Okay, but just here to answer questions. If you have questions, please either post them in the chat or email me your questions. Okay. That's not what I wanted to do. Close that. I need a little bit of help with some Stoic. I can type the question right here. Okay, go ahead and type the question, Aaron. Get a Word document ready. Okay. I'll be right with you. I'm just getting a Word document ready to go here. Just going slow. So what is it? 0.06 grams of aluminum reacts with sulfuric acid. How many grams of aluminum sulfate are produced? Okay. So this is from the stoichiometry packet. Let me get a little bit bigger font. What am I doing? Sorry. Okay. Okay, so the first thing is, again, we know it's stoichiometry because we are given the amount of one thing. In this case, we're given 0.06 grams of aluminum, and we're asked about aluminum sulfate. So it is stoichiometry. You're given the amount of one thing, 0.06 grams of aluminum. Okay, and you want to know how much aluminum sulfate you're going to get. So the first thing we need to do is balance the equation. So you got aluminum plus sulfuric acid. So you got to be able to come up with those formulas. Okay. Right now, it's really more about the stoichiometry. You can go back and review all the nomenclature stuff. But so you have aluminum plus sulfuric acid, and we know one of the products is aluminum sulfate, so we can just go ahead and write down that product, and it would be Al2SO4 3. But aluminum is 3 plus, and sulfate is 2 minus. So it's a 2 to 3 ratio. So that's what aluminum sulfate is. And really, that's kind of all you need to know because it's really going to end up being obviously that whatever the coefficient for aluminum is going to end up being whatever the coefficient of this is times two. So we know the ratio is one of these for every two of those, but it's good to know the whole equation. Okay, so the whole equation is so this is a single replacement reaction. So aluminum is replacing hydrogen, so you're going to get hydrogen gas by itself, right? So now we can go and balance it, right? Again, and this is all just step one. This is balancing the equation, figuring out what your recipe is for the stoichiometry problem, right? So one aluminum, two aluminums. I'll put a two here to begin with. I got two hydrogens. Two hydrogens. I don't need to do anything there, but I got one sulfate. I got three sulfates. So I'm going to have to put a three here. But now that's three times two hydrogens, so I got to go over here and put a three here. Okay. So notice the ratio is 1 to 2 for the aluminum to aluminum sulfate, and that's the ratio we need because we're assuming we have excess sulfuric acid because they didn't tell us how much we had, and the limiting amount is the 0.06 grams of aluminum. Okay, so step two, take what you're given, 0.06 grams of aluminum and convert it to moles. The way we'll do that is we'll we'll divide by the molar mass of aluminum. So the way that would look is like this: one mole aluminum for every, was it 26.98 grams? Okay, and I think that's right. It's just the molar mass on the periodic table. I don't have the periodic table with me right now, so that's really what that would be. All right, so let's take what we're given and convert it to moles, and now we're going to step three, which is the stoichiometric step. We're going to multiply by the mole ratio. And the mole ratio, again, we want the aluminum sulfate, and we have the aluminum. So it's going to be 1 mole of Al2SO4. I'm not going to worry about the subscripts right now because it's just going to take too much time formatting. Over 2 moles of aluminum, right? So we get this ratio 1/2 from our balanced equation. Okay, oops, sorry. Here we go. All right, so that ratio comes from our balanced equation. One of these for every two of those. So that's step three. So now if we do this method, we do 0.06 divided by 26.98, and then we divide by 2, that's going to be how many moles of aluminum sulfate are expected to be produced. So if we go back to the question, it says how many grams. Okay, so now we multiply. Now we have to multiply by the molar mass of aluminum sulfate. So we'd have to add that up. So um, got my calculator. Let's do this real quick. So if you look at the formula, right, for aluminum sulfate, you have 3 times 4. You got 12 oxygens. You have 3 sulfurs and 2 aluminums. So it'll be 2 times 26.98 for aluminum plus, and then it would be 12 times 16 for the oxygen plus 3 times 32, I think it's 0.06 for the sulfur. And so that comes out to be 342.14. So now we just multiply by the molar mass. Okay, and it would be 342.14 grams per 1 mole of the aluminum. I'm not going to write the formula, but so for every 1 mole of this compound, that's how many grams. Okay, so then we do the math, and we end up with 0.06 divided by 26.98 divided by 2 times 342.14, and we get 0.38, but I think we have to end up rounding to like 1 sig dig, so 0.4 grams. Okay. And so that would be the final answer for that question. Okay. All right. I saw somebody email me, so let me check that out. So number 1 on the gas stoichiometry worksheet. Number 1 on the gas stoichiometry worksheet. Okay. Let me open that up real quick. So number 1 on the gas stoich worksheet. Let me find it first. I got stuff all over the place here, so let's figure this out. Gas stoichiometry worksheet. Okay. Let me open that up here. Whenever I stream, my Word documents struggle opening, so I gotta just, come on, it'll work eventually. Maybe I should just open the PDF. I'll open the PDF too, just in case. Which is the key. Okay, here we go. All right. So, just hopefully this is so gas stoichiometry worksheet. Okay, so what volume of CO2 gas is produced when 17 liters of oxygen react with excess carbon monoxide? Okay, so the key is here. Well, okay, so let's talk about the way you really should attack this question. Okay, it's it's the easy way, but it's because you do it this way because you understand how the relationships work. Okay, so here's the deal: when moles of gas. So on the key, I have it set up this way, but you really should just focus on this right here. Okay, we're going from volume of a gas at STP, or not at STP. Forget I said that. We're going from volume of a gas to volume of another gas, and it's key to understand that as long as pressure and temperature don't change, and they're saying that's the temperature and that's the pressure. So we know pressure isn't changing. We know temperature is not changing. So when pressure doesn't change and temperature doesn't change, volume of gas is based on the moles of gas. So the volume ratio and the mole ratio are the same thing. So the easiest thing to do for this question would just be to take 17.0 liters of oxygen, O2, and then just multiply by the mole ratio, which is also the volume ratio when pressure and volume stay the same. So what we would say, what are we looking for? So it would be 2 liters of CO2 for every 1 liter of O2. right? And that ratio, whoops, 1 liter. That ratio right there, and let me make the font bigger. That ratio is the same as the mole ratio from the coefficients in the equation. And as long as you're going from volume of a gas to volume of another gas, and again, they have to be gases, you can use the coefficients in your balanced equation as the mole ratio. Okay. And we kind of did an example like this. Let me show you. If you go to your gas stoichiometry notes, the very first question kind of shows that. Now, it kind of shows why. So, like, this is the gas stoichiometry notes, and it's the same question. You have 15 liters of hydrogen gas, and they want to know how much ammonia gas is going to be produced. So they give you volume of one gas, and they ask for volume of another gas, and you're at STP. So when you're at STP, you know you can use 22.4. But if you're not at standard temperature and pressure, it would. But as long as pressure and temperature remain constant, then then that means that the volume ratio and the mole ratio are the same. And like, so let's look at this. So if we follow our normal steps, so if we went and followed the normal steps for Stoic and didn't know that mole ratio and volume ratio were the same thing, right? We would take our 15 liters of hydrogen, divide by 22.4 because we're at STP here. Then we would do our mole ratio step, and then we would convert to desired units by multiplying by 22.4. Why do we multiply by 22.4? Because again, we're at STP and we're looking for volume of a gas. And so notice that this step and this step cancel each other out. You're dividing by 22.4 and you're multiplying by 22.4. Well, what I'm telling you is it doesn't matter what the temperature and pressure is as long as it remains constant. If you're going from volume of a gas to volume of a gas, you would be dividing by the same numbers, but then multiplying by the same numbers every time. So if you look at this answer key, okay, if you look at the way so the first thing would be take what you so if you didn't want to do the shortcut step, which is this, the first step would be take what you're given and convert to moles. So how do I convert to moles using the ideal gas law? You solve for N. So the ideal gas law says PV equals nRT. So we would so if we wanted to go the long way, we would say, okay, PV equals nRT, and that means N equals PV divided by RT, right? So what are we going to do? Okay, what are we going to do? Let me see. For sorry, after we have the balanced equations, for step two, we would multiply PV and divide that by RT. That would give us our moles, right? That's what N would be. So like, let's not even plug in numbers. We'd be multiplying by the pressure and the volume, right? And we would divide it by RT, okay? All right. But then if you after you do that, after you figured out moles of oxygen, right? So what you would do is take your liters of oxygen, plug it in for volume, take the pressure, plug it into pressure, take the temperature in the Kelvin form, plug it into Kelvin. Our value, if you didn't see, is the 62.36. That's the R value to use when you're at millimeters of mercury. Okay. So that's what you would plug in, right? And then what you would do is once you had n, let me get back to once you solve for n, maybe you would multiply by your mole ratio. You would multiply by the mole ratio in the worksheet, which was 2 to 1, and that would give you moles of CO2. And then once you had moles of CO2, how would you get volume of CO2? You would then plug those moles of CO2 into the ideal gas law and solve for volume. So now in step four, right, in step four of the stoichiometry problem, we would say PV equals nRT, but we would be solving for V. And then we would see that, okay, well, if that's true, then V equals nRT, right, divided by P. Okay, So notice step two, we're dividing by R. Step four, we're multiplying by R, right? Step two, we're dividing by T. Step four, we're multiplying by T. Step two, we're multiplying by P. Step four, we're dividing by P. So in step two, we're multiplying by all these numbers. Step four, we're dividing by all those same numbers. It ends up being the same numbers that you're multiplying and dividing by, so it all cancels out, except for which numbers? Except for this ratio. So the only numbers we're multiplying by is the 2-to-1 ratio. All the other numbers cancel each other out because in one step we're dividing by those numbers, and in the other step we're multiplying by those numbers. Okay? But all that really means is that volume ratio and mole ratio are the same thing when you're talking about gases, and it has to be just gas to gas. You can't compare gas to solid or liquid to solid or something like that. That's when you need densities, right? This only works when you're comparing gases, the volumes of gases, and pressure and temperature stay the same. Okay? Because if pressure and temperature are the same, but volume's different, the only thing that is different then is the moles, right? So, if PV equals nRT, right? If pressure remains constant and temperature remains constant, the only way volume can be different is if N is different, if moles is different, and vice versa. But if pressure and temperature and volume are the same, then moles are the same. Like, so kind of, so just making those concepts. So I hope that answers your question, Jacqueline. Let me know if that helped you. But again, the easiest way is if you're going from volume of a gas to volume of a gas, and they don't mention anything about pressure and temperature changing from before the reaction or after the reaction, then you don't have to worry about the ideal gas law at all. The volume ratio, the mole ratio is the volume ratio. Okay. All right. So Aaron, I hope that answered your question, and Jacqueline, I hope that answered your question. Let me know if you have any more. Okay, so again, just an open forum right now. If you have questions, please ask either in the chat or send me the email. Again, use the fcps.edu one. That's the one. So is the answer from the mole ratio dimensional analysis the answer? Yeah. That's the answer. Like you yeah, so 34 liters. Right? So like when you do it that way, you get 33.9, so that's 34 liters. So either way you do it, you get the same answer. So I'm just showing you that the easiest way is just multiplying by the mole ratio. So yeah, the answer to that question would be 34 liters. Yep. And notice when we do it the other, we get 33.9, so 34 liters, right? If we do it the long way, we get 34 liters. If we do it the short way, we get 34 liters. Okay. So I just kind of like, if this is the way I would suggest you do it. Like, I mean, as soon as you see it's volume of a gas to volume of a gas, and pressure and temperature are the same, then then the particle ratio, the mole ratio, is the same as the volume ratio. Okay, so just use it that way. All right. Yeah, no problem. No problem, Aaron. And remember on Blackboard. I know you can't go on Blackboard right now, but it would be, I guess, in the Unit 5 section. or in somewhere in the assignments, some of the more recent assignment posts, the answer key to the balanced equations for the Stoich packet are are up there. So you can, not the stoichiometry part of it, but you can go check and make sure you have the correct equations and the correct formulas for everything. So you might want to do that. Okay. Once Blackboard's back up. Okay. Yeah, no problem. Jacqueline. Okay. Again, just let me know if you have any questions. I'll hang out for a little bit, wait for a couple questions, but I don't know if many people are more are going to show up. But if you have other questions, don't hesitate to ask about any of the stuff that's been assigned for the week, or you know whatever. Okay, Yeva, could you please answer one of the questions from the beginning of the year? Why does F minus have a larger nuclear charge than O2 minus? Thank you. Okay. Be, because it has one more proton. That's so. So remember, it's about the total. Like so, oxygen has eight. Um, oxygen has oxygen has eight protons in the nucleus, so its total nuclear charge is plus eight, and fluorine has nine protons in the nucleus. So they both have the same number of electrons, right? F minus has the same number of electrons as O2 minus. All right. So F minus is going to have a smaller radius because it's going to be able to pull those 10 electrons closer to its nucleus compared to oxygen because it has one more proton. So remember, Coulombic attraction is based on the distance they can the distance the electrons are from it, but also the magnitude of charge. So this would be more of the magnitude of charge. So because the nucleus of fluorine has a higher magnitude of charge, plus 9 versus plus 8, the 10 electrons around the fluoride ion are going to be pulled closer to the nucleus. And that's, again, that would be explaining why fluoride has the smaller radius, why it would be more difficult to remove an electron from a fluoride ion versus an oxide, even though both would be difficult to remove from, but it would take more energy to remove an electron from a fluoride ion because it has a smaller radius. The electrons are closer because of the greater effective nuclear charge. So it's I mean, essentially all you would have to say it's because F minus has one more. proton, proton in nucleus. Um, so if you want to talk about Coulomb's law, you would say, um, so it's like basically Coulomb's law is Q1 times Q2 divided by R squared, which is just charge one times charge two divided by R squared. That's essentially what the force of attraction is equal to. So Q1 would be represent, one of the charges, and Q2 would be the other charge. So in this case, it would be like Q1 is the charge of the nucleus plus 9 for fluoride's case, and Q2 would be plus or minus 10, right? And so, and it's the absolute value. So it'd be 9 times 10 versus 8 times 10 in terms of that. And that's essentially why it would have a greater nuclear charge. Okay. Okay. So hopefully that answers your question. What else? Anything else? Good review question there. Again, don't hesitate to email. So I'm gonna wait a few more minutes just to see if we get. Okay. Can we also retake a quiz today, or should I wait till Blackboard is working again? Which quiz would you like to retake? Let me know which quiz. I'll look it up. Right now, you could take it because if you're the first one to retake it. The reason why I usually want the 24 hours in advance is because I'm going to tweak some things, each time somebody takes it. But I've only had two quizzes retaken. So if it's a quiz that no one else has retaken yet online, then I can just give you the original retake, and then I'll tweak it next time somebody wants to retake it. So just let me know which quiz, and we could do it right now if you wanted to, and I'll email it to you, and I'll look it up and figure out the time limit. 3.1, yes. You could retake that now. Okay, hold on. Let me figure out how I will do this real quick. So what if I... Okay. Yeah, just hold on. Let me find it, and I will open up my email. You said 3.1, 3.1, 3.1. 3.1 is fine. Let's see, 3.1 retake. All right, yeah, I'm going to open this Word document up real quick. Don't look at your screen for like the next 10 seconds, okay? Hold on. Come on. Open up. Let's go. Yeah, read only, that's fine. Okay. All right, so the deal will be I'm going to email you the quiz right now, and then you will have a total of 30 minutes to take it and email it back. So let me send it your way. Hold on, I gotta open up my email. Yeah, I gotta do that here. So let's see. There. Do this. So and just when I send it to you, you can start. And so like you can either type your answers in it, or you can either type your answers in it, or you can handwrite it your answers and take a picture of them and send me that, or scan a PDF. But essentially, this will be a good kind of test of this will be a good test of what the AP exam is going to be like. So, give yourself 25 minutes to answer the questions and then 5 minutes to get your responses back to me. Okay. So let me find my. Here we go. Okay. All right. So I'm going to send it to you now. So go ahead and work on it and just get it back to me by 1:06. Okay, 1:06. All right. So however you want to get it back, email me or well, hold on. Yeah, go ahead. Okay, yeah, but make that 1:08. You have until 1:08. If you're the only one still watching, obviously ignore me. I'm gonna see if there's anybody else that has questions, but I might shut down the live stream because no one else seems to have questions. But just whenever when you finish by 1:08, go ahead and send me your quiz. Okay. All right. Thanks. All right. So it doesn't seem that there are any more questions. So I think I'm going to end the stream. Again, if you have any questions, don't hesitate to email me. Again, the best email to get an immediate response or, the quickest response is this one, srfox at fcps.edu, not the FCPS schools .net one. But please don't hesitate to email me if you have questions. AP chemistry students, you hopefully check out that the material I posted. I mean, I sent you, two of them I've sent out already, and the third one, the AP chemistry, is just a nice review guide for you. It's got everything in there. It would be good for you seniors. You might want to take that to college just to help you out, especially for those of you for those of you that are going to be taking like chemistry 101 or whatever when they get to college next fall. So that's all. It's a good thing to have, a good reference to have. Okay. So thanks for coming. Thanks for asking questions, and have a good weekend. Okay.